of each other. So this was the Duncan's theorem. After that, we were having the Roth equations. Okay, so the variables for Lagrangian functions or the Lagrangian variables were t, qi and pi. T, qi and qi dot. And the variable pi. After that, Roth proposed that instead of replacing all the generalized velocities with the generalized momentas, we can try a new thing, that some of the generalized velocities can be considered and some can be replaced with the generalized momenta. So he said that consider both type of variables, some Lagrangian and some Hamiltonian. In both the variables t, q1, q2, qn, these are common, so take them as it is. But after that, in Lagrangian there was q1 dot, q2 dot, qn dot, and in Hamiltonian it was p1, p2, pn. So Roth proposed that just consider sum of the q1 dot, q2 dot, qn dots and sum of p1, p2, pns. So he had taken t, qi, q alpha, qi dot and p alpha, where I varies from 1 to m and alpha varies from m plus 1 to n. So Roth proposed the new variables like t, q1, q2, qn, then q1 dot, q2 dot, qm dot, then pm plus 1, pm plus 2 and pn. These were the variables proposed by Roth. And now, according to the definition, p alpha will be curly L by curly q alpha dot. Lcn of L is different from 0. So there will exist a new function, say it will be R. We will define it very soon. And q alpha dot will be curly R by curly p alpha. Also, R will be a function of t, qi's, q alphas, qi dots and p alpha. Defined as R is equal to summation. It will run over those variables which are changing from old to new, and that are p alphas. So p alpha into q alpha dot, where alpha lies from m plus 1 to n, minus L bar. Here this L bar represents that in replace the generalized velocities with the generalized momenta. So it's a function of t, qi's, q alphas, qi dots and p alphas. And now using the Duncan's theorem, this time we are having a new function R, an old function L, new variable p alpha, old variables q alpha dot. And due to Duncan, what we will obtain? Curly R by curly qi dot will be equal to minus curly L by curly qi. These are due to the last term, that the partial derivative of both the functions with respect to the variables, scalar quantities, will be negative of each other. Here R is the new function, L is the old function, and t, qi, q alpha and qi dots, these are the scalar quantities. So curly R by curly qi will be equal to minus curly L by curly qi. Curly R by curly qi dot will be equal to minus curly L by curly qi dot. Curly R by curly q alpha will be equal to minus curly L by curly q alpha. And curly R by curly t will be equal to minus curly L by curly t. Further, all of we know that the Lagrange equation for potential forces were d by dt curly L by curly qi dot minus curly L by curly qi is equal to 0. Now replacing the value of curly L by curly qi dot and curly L by curly qi, we will obtain d by dt of curly R by curly qi dot minus curly L by curly qi is equal to 0. this one, and the last one dp alpha by dt is equal to curly L by curly Q alpha, which is due to the fact that it's obtained in equation number 4. Q alpha dot is equal to curly R by curly P alpha. Okay, so these terms, now we are having these 3 type of equations. The first one, d by dt of curly R by curly Qi dot minus curly R by curly Qi is equal to 0. dp alpha by dt is equal to minus curly R by curly Q alpha dot, and dq alpha by dt is equal to minus curly R by curly P alpha. These are known as the Roth equations. Okay, so after that there is a definition of cyclic coordinates, or we can say that these are termed as ignorable coordinates. Those coordinates for which the system is independent from those coordinates, or those coordinates which does not exist explicitly in the expression of the problem or the constraint equations or anywhere, are known as the ignorable or cyclic. Means if we can skip those coordinates, we can ignore them, okay, are known as the cyclic or ignorable coordinates. Okay, after that, let me share a new PDF. Now let's define the new term, that is the Hamilton action. Here we consider an arbitrary holonomic system with independent coordinates q1, q2, qn, and the Lagrangian function to be a function of t, qi and qi dots. Then the integral w is equal to integration t0 to t1 L dt is known as the Hamilton action during the time interval t0 to t1. The expression this LDT is the elementary Hamilton action. So if the Lagrangian function is integrated with respect to t over some interval, that quantity is known as the Hamilton action. Okay. Further, all of we know that the displacement is a function of t, so this qi is always a function of t. Now we are going to discuss about the variation of Hamilton action. The variation during some movement of the particles, and if the particles are moving, if some movement is going on, then there will be some initial position and there will be some final position. And if we are talking about that, we are find out the variation at the time interval t0 to t1, it means at time t0 it will be the initial position, and at time t1 it will be the final position. So assume qi naught be the given initial position of the system at time t is equal to t0, and qi1 be the given final position at the time t is equal to t1. First of all, we are just fixing the initial and terminal positions. Means we are assuming that the initial position of all the particles are same and the final positions are similar. Means there is no variation. Otherwise, the particles can move. Now, if we are working in some plane, however, we are going to work in n+1 dimensional space. Why it is n+1 dimensional? Because we are having n+1 coordinates. One is t, then q1, q2, qn. Total n+1 coordinates. And now from time t no, from qi naught to qi1 means from final position to from initial position to final position, we can move through various paths. Like we can move on a straight line path, we can move from any arbitrary path that is not straight. Okay, so there is a concept of straight paths and circuitous paths. That if we are moving from initial position to final position along a straight line or along a straight line path, then that very path is termed as straight path. Otherwise, the remaining all the possible paths are known as circuitous paths. No diagram is represented. I will share a diagram in which it will be elaborated that what do we mean by a straight line path and a circuitous path. Okay, there is one more term that along a straight line path the Lagrange equation of motion is satisfied. Means d by dt curly L by curly qi dot minus curly L by curly qi will be equal to 0 along a straight line path. And now we are having the Hamilton principle. It states that the Hamilton action W will have a stationary value for a straight path. Stationary value means its variation will be 0. There is no variation in the Hamilton action along a straight line path. And for that, we are just assuming that a one parameter family qi is equal to qi t alpha. Why we are introducing this alpha? Because due to alpha, the paths will be changed. We are assuming that when alpha is equal to 0, the path will be straight line path. But when it is non-zero, the path obtained will be a circuitous path. Now we are taking that the initial position and final position are fixed. So all the paths have a common initial point, say M0, and a common end point, say M1. And it will be obtained at time t0, means qi t0 alpha will be qi0 and qi t1 alpha will be qi1. It will be independent of alpha. Now the Hamilton action W, when the Lagrangian function L is integrated over time naught t0 to t1 with respect to t, then after integrating, we will replace t with t1 and t0, which are the scalar quantities. So when we will solve the right hand side of equation number 7, what we will obtain, that the term that remained will be a function of alpha only. However, there are two variables present. One is t, second is alpha. But we will integrate this quantity with respect to t, and then we will replace t with final limit and with initial limit, upper limit and lower limit. So t is replaced by the scalar terms. So there will be no t. The remaining term will be a function of alpha only, and that's why we had written W alpha is equal to integration t0 to t1 L t qi t alpha and qi dot t alpha dt. And now let's find out the variation. And let me remind you one thing, that this variation is with respect to alpha. Why? Because alpha W is a function of alpha only. So it will be t0 to variation of L dt. And one term that is not written here, actually Leibniz rule is applied. We were to find out variation of W L, but there are two more terms, plus in L t is replaced with upper limit and then variation of t1, minus in L t is replaced with t0 and then variation of t0. But T naught and T1, these are the fixed quantities. So variation of T1 and variation of T naught will be 0. That's why those two terms are not written. And now variation of L, what it will be? T is a fixed quantity. Now L is a function of T, Qi and Qi dots, in which T is a fixed quantity. So to find out the variation with respect to alpha, what we are to do? We will find out the variation of L with respect to Qi, and then variation of Qi with respect to alpha, plus variation of L with respect to Qi dot, and then variation of Qi dot with respect to alpha dt. Right hand side of variation. And now what is this? Is then del W is this. Now del Qi dot, it will be variation of derivative of Qi T alpha. This is not D, this is alpha. So it is variation with respect to alpha. So partial derivative with respect to alpha, d by dt Qi T alpha delta alpha. And it will be d by dt, partial derivative and the total derivative are interchanged. Curly by curly alpha Qi T alpha del alpha, and which is d by dt of del alpha. So del Qi dot is d by dt of del Qi. Replace this in delta W, right hand side of delta W. What we will obtain on right hand side? We are having integration T naught to T1 summation I from 1 to n curly L by curly Qi del Qi plus curly L by curly Qi dot d by dt of del Qi dt. We are solving the second integration of the second term, and it will be integration T naught to T1 summation I from 1 to n curly L by curly Qi dot del Qi dot dt, which is equal to integration T naught to T1 summation I from 1 to n curly L by curly Qi dot d by dt of del Qi dt. Now we are having two functions. First is curly L by curly Qi and second is d by dt of del Qi. So using integration by del Qi T naught to T1 minus integration T naught to T1 derivative of first term summation I from 1 to n d by dt of curly L by curly Qi dot into integration of second. So it is del Qi dt. And now T1, and at T1 it is the
सर
final
आपकी
position.
वॉइस ब्रेक हो रही है बीच में.
Okay. Sorry. Okay. Now when T is equal to T1, then Qi at T is equal to T1, it's the final position. And so its variation will be 0 because that is fixed. As we assumed that the initial position and final positions are fixed. So at T is equal to T1, del Qi is 0 because it's the variation of the final position, which is a fixed term. Similarly, when T is equal to T naught, it's the variation of the initial position, which is again fixed. So the first quantity on right hand side is 0. And what is remained? It's minus integration T naught to T1 summation I from 1 to n d by dt of curly L by curly Qi dot del Qi dt. It is written since the variations are 0 at T naught and T1. Now replace this quantity in del W. So del W is integration T naught to T1 summation I from 1 to n curly L by curly Qi minus d by dt curly L by curly Qi dot del Qi common and then dt. And now if we people are discussing about a straight line path, then along a straight line path the Lagrange equation is satisfied. means d by dt of curly L by curly qi dot minus curly L by curly qi is 0. So the quantity on right hand side is 0. It means variation of W is 0. So along a straight line path, the variation of the Hamilton action is 0. It means the Hamilton action will have a stationary value. Is it okay? So this is the result. I think enough for today. We will start it tomorrow. One thing, that its converse is also true. Means if the variation is 0, then the path will be a straight line path. Any problem from your side?